Suppose I start with x1 to xk that have joint distribution multinomial in p1 to pk. My question now is, what is the marginal distribution of x1? Now again we can just start with that joint PMF and then try to sum and get something complicated and finally simplify to get this, but we can use the definition in terms of random experiment and get it immediately. It's like this. Here you are rolling a k-faced die, so the possible outcomes are 1, 2, 3 up to k with probabilities. Now when I say I want to look at only x1, this means I am merely counting how many times I get 1. So basically I am partitioning. 1 is in one group and all the rest that are not equal to 1 are in the other group. So it is just like tossing a coin, where if I get 1 I call it head, and if I do not get 1, that is I get any of these other k minus 1 things, I just call it a tail. Then the probability of head is p1, while the probability of tail is p2, p3, etc. up to pk, which can be abbreviated to 1 minus p1. So x1 naturally will be like tossing a coin n times with probability of head equal to p1. So I immediately know that this must be binomial in p1. And obviously there is nothing profound about 1. The same argument can be applied to any other I. So it is xi marginally has binomial in pi distribution. And immediately I can conclude that expected value of xi is n pi and variance of xi is n times pi times 1 minus pi. These are coming directly from properties of binomial distribution. Now the argument that allows us to compute the marginal distribution of each xi can be extended to other marginals also. Suppose I ask the question, what is the joint distribution of x1 and x3 say? Of course I assume k is greater than or equal to 3 for this. Well, again you consider the same way. I have the k-faced die with these probabilities. Now I am focusing on only 1 and 3, 1 and 3 and the rest. So all these things are lumped in one group. So it is basically like I am reducing it to a three-faced die. One face shows 1, another face shows 3, and the third face has all these other k minus 2 faces lumped together. In that case, the probability of 1 is p1, probability of 3 is p3, and probability of all the others lumped together is the sum of these quantities. Once you think in this way, it should be just immediately apparent that multinomial n, p1, p3 and all the things lumped together, that is 1 minus p1 minus p3. Now there is a little problem in our notation, because in our notation we are having as many xi's as there are pi's. Here I have got three things, three-faced die. So here also we should have actually three things. So we should better write x1, x3, comma, n minus x1 minus x3. It is just to satisfy our notation. So the randomness here is only in x1 and x3 because this is completely determined by the first two components. So from this you are getting actually the marginal of x1 and x3. We again start with x1 to xk, multinomial in p1 to pk. This time our aim is to find covariance xi xj when I is not equal to j. We can naturally guess that it should be something negative because all these things must add up to n. So if xi becomes very large, xj does not have enough space to grow. So a large value of xi will naturally be associated with smaller values of xj. So it should be negative. We want to explicitly compute it. Again, instead of using the PMF directly, we shall employ a little trick. The trick is the following. Let's consider these n rolls of our k-faced die separately. So suppose I take only one roll. In that case, exactly one of them is 1, all the others are zeros. Now I will consider another roll. So again I have got y1 to yk, exactly one of them is 0 and exactly one of them is 1 and the others are equal to 0. And there are two different roles, so I have assumed that they are independent. In that case, the expectation that x of xi times yi, remember all these things are indicators, either 1 or 0. So this is also 1 or 0. So its expectation is this probability that this is 1. And this will be 1 if and only both of them are equal to 1. So what is the probability that xi equals 1? So in this role you have got the face I. And this is 1 if in the second role also you got that face. They are independent, so it will be pi squared. Now if I is not equal to j, the argument is very similar. Again, they are independent, so the expectation just splits. This one is 1, probability pi, and that one is 1, is probability pj, so it is pi times pj. So both the things are actually of the same form. I might as well drop this condition. Now consider expectation of xi times xj when I is not equal to j. Remember, exactly one of them is 1. So out of this, at least one is 0. So the product must be 0. So this is just equal to 0. But if I is equal to j, then it is expectation of xi squared, but since it is a 0 and 1, so its square is equal to itself, so it is just same as pi. So when you are working within x's or similarly within the y's, then I not equal to j or I equal to j makes a difference. But when you are doing the cross things, one x and another y, you have this general formula. Now we get back to our original problem where I had n. And as I said, I am going to consider all the n roles separately. Accordingly, I shall start a new notation. For the jth role, I will consider the outcomes x1j, xkj. These are all indicators. Exactly one of them is 1. That's why I have written 1. J goes from 1 to n, and these are all independent because I have rolled it n times independently. And how are these things related with this? Obvious. You just keep on adding all these x1s. Then you have x1j, sum over j from 1 to n, that will be your x1. Nothing special about 1, it could be any I, where I is from 1 to k. So now we are ready to tackle finding the covariance. So the main thing that you have to find out to compute the covariance is expectation of xi times xj, which is expectation of product of the two sums. Now this the indices are a little confusing here. Here I am considering xi and xj, they are two components. So I need some index to run over the different roles. For this I have called it R, and for this I have called it S. Now once you form the product, there are n square possible terms and they are products of this form. Now expectation of course enters into the summation, and it is here that I get to use those earlier results. Now here R can go from 1 to n, S can go from 1 to n. I split this thing into two groups where R and S are both same, kind of going down the diagonal, and when R and S are different, that is all the off-diagonal things. Let's tackle the off-diagonal things first, because when I am saying R and S are not same, I am talking about a product of two things coming from two different roles, so they are independent. I know that it will be always pi times pj. And when I am talking about the same role, I know that both these things cannot be non-zero together because I is not equal to j. So I know this part must just vanish. Now you also notice that this has nothing to do with R or S, so it just comes out, and you have to count how many such cases are there. There are obviously n into n minus 1 such pairs are S. So we find that expected value of xi xj equals this when I is not equal to j. Now finding the covariance is trivial, because covariance is equal to this quantity minus expected value of xi times expected value of xj. Just now we have seen it is equal to, and we also know that this is pi and this is pj. So the entire thing turns out to be actually this is actually n times pi and this is n times pj. So it is n square times pi times pj. So this is simply minus n pi pj, which is indeed negative as we had expected it to be.